Imagine we have a cloud of data points scattered across the screen. They don't line up perfectly, but you can tell they roughly follow a certain direction. Suppose the horizontal axis represents height, the vertical axis represents weight. Each point stands for a person's height and weight. Now, the question is, can we use the height to predict the weight? What kind of relationship exists between height and weight? And can that relationship be simplified as just a straight line? That's what exactly linear regression is trying to figure out. We want to draw a line that runs through this cloud of points. Not every point needs to be landing on the line, but the line should come as close as possible overall. This line captures the trend, or a simple way to explain how the two variables are related. We can express this line with the familiar equation. This is the slope-intercept form of a straight line. B0 is the intercept, and B1 is the slope. Notice that we are putting a little hat on y, call it y hat. That is because we're reserving y for the actual observed values shown by the dots. The y-hat values are our estimates, the points that lie on the right line. Now let's take a look at how the intercept B0 and the slope B1 affect the shape of a line. The intercept B0 determines where the line crosses the vertical axis, also known as the y-intercept. When we keep the slope B1 fixed, changing the intercept B0 just shifts the whole line up or down without changing its tilt. When B0 is negative, the line crosses the vertical axis below the origin. When B0 is positive, it crosses above the origin. B1 controls how steep the line is. If we keep the intercept B0 fixed, changing the slope B1 rotates the line around that intercept point. The larger the absolute value of B1, the steeper the line becomes. If B1 is 0, the line is perfectly horizontal. If B1 is positive, the line chews upward from left to right. If B1 is negative, the line chews downward from left to right. The difference between y and y-hat is called the residual. It measures how far off our model is from reality. So the next step is, how do we pick the best values for B0 and B1 that make the residuals as small as possible? In other words, make that red line hug the cloud as closely as it can. In this video, we'll use vector projection to solve for B0 and B1. Imagine writing all the height values as a column vector, and we call it x1 vector. Do the same for the weight values, that's another column vector. We call it y. The predicted values that lie on the red line form another vector, we call it y-hat. The difference between actual y and the predicted y-hat give us the residual vector, epsilon. Now comes a key geometric insight. The vector y-hat lies exactly in the plane spanned by all1's vector and x1 vector. What does that mean? Think of vector of all 1's and x1 vector as forming a two-dimensional plane in the space. The vector y-hat lies right on that plane. But the actual vector y does not necessarily lie in this plane. What we're doing is projecting y orthogonally onto that plane. The result of that projection is y-hat. And the part of y that sticks out of the plane, that is epsilon, the residual vector. Because epsilon is orthogonal to the plane, it must be perpendicular to both all1's vector and x1 vector. These two perpendicular conditions are exactly what led us to solve for B0 and B1. Alright, so now we're using orthogonal projection to figure out B0 and B1. The vector y hat is basically just a linear combination of all ones column vector and x1. So we can write it like you see on the screen. And of course, we can also express this neatly as a matrix multiplication. The matrix you're seeing here, X, is what we call the design matrix. Usually in the design matrix, the first column is just all ones column vector. This is how we represent the intercept term. So the vector y is the sum of vector y hat and the residual vector epsilon, which means the residual vector epsilon can be expressed as shown on the screen. Now here's the key. Vector epsilon is perpendicular to every column of matrix X. That gives us two matrix multiplication relationships. Now we can combine those two into one single elegant matrix multiplication. If we plug in the epsilon and simplify it a little bit, we end up with this tidy equation. Remember, we assumed that all ones column vector and x1 are linearly independent. So the design matrix X has full column rank. This means its grand matrix X transpose times X is invertible. And from this, we can finally derive the closed form solution for vector B. Thus, we get the solution for B0 and B1.